Hello and welcome! In this lecture we're going to implement the A-star pathfinding algorithm. Okay, so let's open up the pathfinding script. And over here let's make our main function to calculate a path. So let's make it public. We're going to return a list of grid position. And we're going to call this find path. For the parameters, we're going to receive a grid position for the start grid position. And another grid position for the end grid position. So here we calculate the path and then we return the entire path. Now, first of all, according to the overview of the algorithm that we saw, first up we have to set up the open and close lists. So let's define a list of path node for the open list. Let's create the list, and same thing for the close list. So like I said in the overview video, the open list contains all of the nodes that are queued up for searching, and the closed list, this one contains all of the nodes that we have already searched. So in order to start up our algorithm, let's add the start node onto the open list. So first we get the start node, so the path node for the start node, and we're going to go into the grid system in order to get the grid object on the start grid position. So we get the start node, then go into the open list, and we add the start node. The next step to initializing the algorithm is we first need to cycle through all of the nodes and reset their state. So let's do a cycle through the x and the z. So for int x equals 0, go into the grid system to get the width. Then do another for the int z equals 0. And let's do z under the get height. Also, by the way, in the beginning of this script, we define these fields up here. We're actually going to set them when we make the connection with the level grid, so that we only define these values once. So we're going to handle that in a bit, so that is why these are defined here, but for now let's just keep going with this. So we cycle through all of the path nodes in our grid system. Now let's get the path node grid object for this one, so the path node, and from this one let's go into the grid system, and on the grid system let's get the grid object, which is the path node. Get the one for this grid position, so a grid position for this grid position, a new one with this x, this z, and we use this to get the grid object. Okay, so we have the path node object. Now here let's initialize it. So first thing we want to do is to reset the g cost to infinite. The g cost, if you remember, that is the cost from the walking node onto this node. So we default to a super high value and then recalculate it when we get to this node. So that means we need to expose some function to set the g cost. So let's do that. Let's go into the path node script, and up here let's make that function. So a public void set g cost, receive an int for the g cost. And then we're also going to need one for the h cost. So let's do that as well. So set the h cost, int h cost, and we just set it. Okay, and finally for the f cost, we're not going to manually set it. Instead, like we saw, the f cost is g plus h. So instead of having a function to set the f cost, let's just make a function to calculate the f cost. Then just do the f cost equals g cost plus the h cost. Okay, so we've got all the public functions that we need. Back into the pathfinding script, let's set the g cost. Like I said, we want to reset this to the max value. So for that, we can use the constant int.maxValue. Then for the h cost is the heuristic to reach a target. So when we initialize it, let's initialize the heuristic at 0. So set the h cost to 0. And finally, we can also go into the path node in order to calculate the f cost. Then the next thing we need is to reset the came from node, since we don't want the results of the last pathfinding to influence this one. So for that, let's go into the path node script, and up here let's make that function. So public void reset came from path node, and we're just going to set the came from path node, set it to null. So then on the pathfinding script, let's just go path node in order to reset the came from node. Okay, so with this, we are correctly initializing all of the nodes on our pathfinding. After this, we can finally start searching for a path. So first up, let's set up the starting node. We want to calculate all of the costs for the start node. So first thing is we want to set the g cost. And again, the g cost is the cost of moving from the start node to the one that we're currently testing. Now, since this node, the one that we're currently testing, is the start node, then the g cost is 0. Then we want to set the h cost. And for this one, this is the heuristic, which is a very basic guess to see how close it is to the final node. So let's make a function to calculate that. Let's make public, we're going to return int. And as I mentioned in the overview video, for the heuristic, this is just a very basic, very rough guess. And for this, we are simply going to calculate the distance directly from start to the end. So let's just call it calculate distance. We're going to receive a grid position for the grid position A, another grid position for the grid position B. Then here we can calculate the grid position for the grid position distance. We can just do grid position A minus grid position B. With that, we have essentially the distance, except this might have negative values, so we need to calculate the proper distance, and that is going to be just use mathf.abs in order to get the absolute value, going to the grid position distance.x, and then add the mathf.abs of the grid position distance.z. Then we just return this. Okay, so that's it. Again, super simple, just calculating the straight distance, so there are no walls, no nothing. However, what we have here is the distance in terms of grid position distance, whereas in our algorithm, we're going to want to play around with the unit distance. So that is, like I mentioned in the overview, so moving straight will have a cost of 10, but moving diagonally will have a cost of 14. So those are the kind of values that we want to use here. So in order to define those movement costs, let's go up to the top of the file, let's define some constants. So a private const int, let's call the move straight cost and put it at 10. And finally the move diagonal cost. And this one is 14. Again, if you don't remember what I mentioned, the reason why it's 10 and 14 is because actually it should be 1 and 1.4. It would be that if we were using grid positions directly. However, in order to make the code simpler, here I just multiplied by 10 in order to be able to use ints and not have to use 1.4. And the reason why it would be 1.4 is simply because that is the square root of 2. So you've got the horizontal movement, that is 1, the vertical movement, that is 1. In order to get the diagonal, you do the square root of 1 plus 1, square root of 2 equals 1.4. So again, here just multiplied by 10, so that is why we have 14. Okay, so now that we have this, for this one, for calculating the distance, we are just going through the x and the z, so we have no diagonals here. So in this case, the distance is always going to be straight, so just the distance multiplied by the straight cost. So we do that, and then in here we can use that, so calculate the distance. And again, the age, this is a heuristic from the start to the end, so we calculate the distance between the start node and the end node. So that's the start grid position and end grid position. Alright, so that's the h cost, and finally we just need the f cost, so the start node, and let's calculate the f cost. Okay, so we have calculated all of the costs for this node. With this now we can finally open up our cycle, and like we saw, we're going to keep running the algorithm whilst the open list has some elements. So while the open list.count, while that is bigger than 0, that means we still have nodes to search. First thing we do is grab the current node, so that is a path node for the current node. We go into the open list and we grab it. However, we don't just want to grab the first one on the list. Instead, what we really want is we want to grab the node on the open list that has the lowest f cost. This is how we prioritize the nodes in order to get the algorithm to finish quickly. So let's make a function to do just that. So up here, let's make a private. We're going to return a path node. We call it get lowest f cost path node. And as a parameter, we receive a list of path node for the path node list. Okay, so here we just do a simple cycle just to find out the lowest path node. So let's define a path node for the lowest f cost path node, and we just grab the very first one on the list. Then we just cycle through the list. And we just test if the one that we're currently searching, so on index I, if this one dot get f cost has a lower f cost than the current lowest f cost. If so, then this new one is the lowest one, so let's assign the lowest one to this one. Okay, so we just do that, cycle through the whole list, and then return the lowest f cost. Okay, so that's it, a pretty simple function. So now up here, instead of grabbing the very first one from the list, let's use this one. Pass in the open list as the searching list. Then here, the first check that we're going to do is checking if the current node is already our final node. So let's also grab a reference to the final node. So we've got a path node for the start node. Let's grab the end node. So from the end grid position. So now we've got a reference to the end node. So then here we just check if the current node equals the end node, then here we have essentially reached the final node. And with this, then here's where we're going to calculate the path. So let's return a function that we're going to make. So calculate path, and we're going to need to know where to start from. So let's say the end node. So we're going to make this function in a little bit, but for now, let's continue. So we're searching through and we're currently analyzing this current node. So first thing we do is we remove this node from the open list and add it to the closed list. So go into the open list and let's remove the current node. Then onto the closed list, let's add the current node. So this indicates that we have already searched through this node. Now we need to search through all of the neighbors for this node. So let's make a function to get those neighbors. Let's go down here, make that function. So we're going to return a list of path node and let's call it get neighbor list. Let's receive a path node for the current node. Then here we just define a list of path node. This is going to be the neighbor list. Let's initialize it, and at the end of the function we're going to return the neighbor list. And then here let's just add all the neighbors. So for example, starting off with the node on the left side, let's grab the grid position for this current node. So going to the current node in order to get the grid position, let's make that function. So over here on the path node, we need to expose this, so let's do that. So a public grid position for the get grid position, and we just return the grid position, okay. Then over here we have this, so like I said, let's first grab the one on the left side. So on the neighbor list, we're going to add, then we need to get the node, and we want to get the node that is on grid position.x minus 1, so right to the left, and grid position.z. So let's make this function to get a node for a given x and z. So private path node, call it get node. We're going to receive an int for the x and an int for the z. Then here we just go into the grid system in order to get the grid object. And we're going to get it on a certain grid position. So let's make the grid position with x and z. So we get this and return it. Okay, so now we have this function. So we can feed it an x and a z and we have it. So here first up we have the left node. So x minus 1 and just a z. Let's make the direct neighbors right away. So we got the left, right, up, down. So let's do the right, the up, and the down. For the right, that is x plus 1. For these other ones, let's put x plus 0 since it's on the exact same x. Putting plus 0 just to keep the code nice and organized. So going down, that would be z minus 1. And going up would be z plus 1. And for these, again, just to keep the code nice and clean, put everything like that. All right, so we have all these neighbors, left, right, up, down. And now here, if you wanted or did not want any diagonal movement, if you didn't want that, then you would do just this, so just get these neighbors. But if you do want diagonal movement, then this is where you add it. So here, if we go for diagonal, let's grab the left down and left up. So left down, and then we have left up. So for the left down, we go into the left, going down, let's go minus 1 on the z. And going up, let's go plus 1. Then for the right, let's also add those two. So we have the right down and right up. Right down, so that's z minus 1, and right up, z plus 1. Okay, so here we have 1, 2, 3, 4, 5, 6, 7, and 8 neighbors. So these are all of them. However, like this, we're actually going to have a bunch of errors. Let's say we are testing the grid position 0, 0. Well, if we try to get the one on grid position minus 1, that is going to be an error. So let's add some quick checks to make sure that these positions are valid. So first up, we can actually group all of the left ones. So up here, let's test if grid position dot x, if this one minus 1, so we're testing on the left, if this one is still above or equal to 0. If so, then the left part of all of these is going to be valid. Then for testing all of the right ones, so we test the grid position dot x plus 1, if this one is still under the height. So let's go into the grid system in order to get the height. So if so, then the right portion of all of these is correct. Then for testing up and down, so this one doesn't require any more checks, but this one you need to make sure that z minus 1 doesn't go under 0. So here we need to check if the grid position dot z, if we do a minus 1, if that is still above or equal to 0, then this is valid. And finally for this one, test the grid position dot z. Test if it's under the grid system dot get height. If so, then this is valid. And actually here I made a mistake. We're testing the x, so the x is with the width, not the height. Okay, so all of the lefts are correct, and over here all of the rights. So first of all, testing -1. So we're going to do the exact same thing as this. So let's go, copy paste that one, open and close, and then check if it's under the height. So we do that, open and close. Okay, so we added all the checks, so we know for certain that these will only add neighbors that actually exist. And finally, we just need to check these. So these are the same thing. Let's put it down above it just to keep the same pattern. So let's copy this one, close the bracket, then for this one, and close. And actually here, I also forgot to add +1. So these are quite a lot of numbers, quite a lot tricky, so do make sure there are no issues here. Okay, so check grid position.x -1, it is above 0, okay, great. Then the z -1, it's above 0, that's correct. Z +1 under the height, that's correct. X +1 under the width, correct. Z -1 above 0, correct. Z +1 under height, correct. Z -1 above 0, yes. Z +1 under height, so on. Okay, so we have all of the checks in order to get all of the neighbors for a certain current node. We have the neighbor list, so back into our algorithm, now we can get a list of all of the neighbors. So let's cycle through it. So let's do a for each path node. This is going to be the neighbor node, and we're going to cycle through the neighbor list for the current node. We're cycling through all the neighbors. Then the first thing we do is we check if this neighbor is already on the closed list, meaning if we have already searched it. So if the closed list contains this neighbor node, if so, then we're going to continue since we already searched this one. If not, we keep going. And first thing we do is we calculate a tentative G cost. This is going to be based on the G cost of the current node plus the movement cost to move to this neighbor node. So an int for the tentative G cost. And here we get the current node.get the G cost. So this is the actual cost. And then we add whatever it is, the cost going from the current node onto this neighbor node. So let's calculate the distance between the current node.get position and the neighbor.get position. However, here we actually need to recalculate the distance in order to also take into account the diagonal movement. Over here, how we calculate it is we just use the move straight cost. So let's change this code to take into account both the straight and the diagonal cost. Basically what we have here is the total distance on the x and the total distance on the z. So for example, if we're going from 0, 0 to 1, 1, then we're going to have 1 and 1. So that could either be two straight costs, or it could be just a single diagonal cost. Basically, we can cancel out each horizontal cost on the x and on the z by a single diagonal cost. So here, instead of just calculating the total distance with the x and the z, let's define an int for just the x distance. And we just do a mathf.abs on the grid position distance.x. Then same thing for the z distance, we just get this one, so we get these two separate. Then essentially we're going to move diagonally for as many of the x's as we have z's. Meaning if we have 1 and 1, then that really means just one diagonal. So instead of two straight movements, we've got one diagonal. And if we have 1 and then 2, then that is still just one diagonal. So meaning that what we want is the move diagonal cost multiplied by, let's do a mathf.min. So we grab the minimum between the x distance and the z distance. So with that, we have all of the diagonal movement. Then all that's left is the straight movement. So that is really just the remainder of these. So let's call an int for the remaining. And we just do x distance minus the z distance. And once again, careful with under 0, so mathf.abs. So we've got the remaining distance, remaining after the diagonal movement. So we do this plus the move straight cost multiplied by the remaining movement. And we no longer need the total distance. Okay, so with this we are calculating a heuristic for the distance whilst taking into account both straight movement and diagonal movement. Okay, so now we can continue. So we have our tentative G cost. So we use the current G cost, and then we add the distance of going from the current node onto this neighbor node. Then here, let's do an if. So if the tentative G cost, if this one is less than the neighbor node.G cost, if so, then that means we have essentially found a better path to go into this neighbor node from our current node. So maybe previously we were doing two straight movements in order to get the neighbor node, and now we can do it with just one diagonal. So let's update this neighbor node to say that the best approach is to come from the current node. So we go into the neighbor node and we're going to update the came from node. So let's actually do that function. We already have one to reset the came from path node, so let's make a public void set came from path node, receive a path node, and we just do the came from path node equals this path node. So back into the pathfinding, set the came from path node, and we're going to come from the current node. Then let's update the gcost. So neighbor node, set the gcost. Let's set it to this tentative gcost. And finally, let's also update the hcost. So neighbor node, let's set the hcost. And this one is going to be the usual. So we calculate the distance from this neighbor node. So this one dot get grid position onto the end grid position. And finally, of course, we need to recalculate the fcost. So calculate the fcost. All right, so we have updated this node. Then let's just check. So if the open list does not contain, if it does not yet contain this neighbor node, then let's go into the open list and add this neighbor node onto the open list. All right, so this is the complete cycle. So going back to the beginning, so we cycle through all the nodes on the open list. So while we have nodes there, then we're going to do this. We grab the current node, which is going to be the one on the list that has the lowest fcost. This is how we prioritize it. Then first we check if the current node is the final node. If so, then we already have our path, so we calculate the return path. If not, then we take this node from the open list and we add it to the closed list in order to signify that we have already tested the current node. Then for this one, we check all of the neighbors on this node. If they're already on the closed list, then that means we have already searched them, so we ignore them. If not, then the first thing we do is we calculate a tentative gcost. That is the cost going from the start node to this neighbor node. If it is smaller, then that means moving from this current node to this neighbor is faster than whatever the neighbor was previously testing. If so, then we update the neighbor with the new stats. And if the neighbor is not yet on the open list, we add it so we can search it. So that's the entire cycle, and if we reach down here outside of our while, if so, then that means we no longer have any more open nodes, but we also did not reach the target. So that means we searched through the whole map and we could not find a path. So you get over here, then no path found, and let's return null. Okay, so this is the whole algorithm. Final thing we need is just to implement this function to calculate a path. So let's make that one. Let's go down here. So let's make it private. We're going to return a list of grid position. Call it the calculate path, and we're going to receive a path node for the end node. Then here, let's create a list of path node. Call it the path node list. We're going to instantiate it, and right away we're going to add the end node onto it. So let's add the end node. Then we're going to need to cycle through it and pretty much walk backwards. So let's start off with a path node for the current node that we're going to check, and let's start off on the end node. Then let's do a while the current node, and let's get the came from path node. So let's actually make that function. So instead of set, let's make a get. So get the came from path node, return a path node, and we just return the came from path node. Okay, like this. So here, let's get the came from path node. So while this one is not null, then that means this has some node connected to it. And if so, then let's go into the path node list and let's add, go into the current node and get the came from path node. We do that, and then we update the current node to be this one dot get came from path node. So we start on the final node, then we check if this one has any node linked to it. If so, then we add that linked node onto the list and we make that linked node the new current node. Then we cycle through again on that linked node, see if that one also has a link, and so on and so on. So with this, we have our complete list with all of the path nodes that are connected. That is essentially the path. However, here you can see that we started on the end node. So basically the node on index 0 is going to be the final node, and the one at the end of the list is going to be the actual first node. So that's very simple. We can just reverse it. So just go into the path node list and call reverse. So with this, we have the final path node list. Now the function is meant to return a list of grid positions. So let's make that. So the grid position list, we make a new one. Then we just cycle through path node, in the path node list. Cycle through all of them. Then on the grid position list, let's add, go into the path node in order to get the grid position. So we do that, we have the grid position list, and then just return the grid position list. All right, that's it. So here is everything that we've done. So we wrote quite a lot of code, but the algorithm should be implemented. So let's test and see if it all works. Now for testing, let's go into our very helpful testing script. So let's go up here onto this one. Let's test it over here when we press the T key. So when we do, let's calculate the path towards the mouse position. So let's get a grid position for the mouse grid position. And the same as we've done so many times before. So go into the level grid, the instance, in order to get the grid position. Let's go into the mouse whirl in order to get the mouse whirl position. Okay, so we have the mouse grid position. Then let's calculate the path going from 0 onto this. So let's actually do a grid position for the start grid position, starting off on 0, 0. Then we need to go into the pathfinding script and we need to access the instance. So let's actually make that. Once again, we can copy the very first singleton that we made on the unit detection system. So up here, let's go. We copy the instance. So let's go into the pathfinding up top. Let's drop the instance, just change the type. And then also the one on awake. So let's grab this one on pathfinding. Let's paste that one. So actually we already have an awake. So let's copy and paste it in there. Okay, so we have the instance. Let's just change the name here. All right, so we now have our static instance. So on testing for pathfinding, let's go to the static instance and we're going to call find path. Let's pass in the start grid position and the mouse grid position as the end. So we do this and this returns a list of grid positions. So the grid position list. And now just to be able to see it, we can actually do debug.drawLine in order to visually see the path. So let's just cycle through it. So do a for int for the grid position list.count. Let's go I++. Then here we do a debug.drawLine. Let's draw a line from this grid position onto the next one. So for that, we're going to need to go into the level grid, the instance. In this case, we want the world position, the world position of grid position list on this index. And the second one is the second position on the draw line. So for this one, let's go into grid position +1. However, if we're using +1, then we need to make sure that we do the cycle until less than 1. Just to make sure that even on the final element, we still have a +1. Okay, so those are the one, the start, the end. Then for the color, let's do color.white. And then for the duration, let's say 10 seconds. All right, so that should do it. So when we press the T key, we should be able to visually see the path going from grid position 0, 0 onto wherever the mouse is. So let's see. All right, so here we are. And let's see, so if I place the mouse somewhere, and actually, first of all, we need to enable gizmos. So on the top right corner, we see a gizmos button. So if you toggle it, yep, we see the gizmos. We use debug.drawLine, that is a type of gizmo. So we need to enable it in order to see the line. Then also right now, all of the text objects are really huge. So in order to be able to easily see the path, click on the little arrow next to the gizmos. Make sure that 3D icons is ticked. And then over here, just make them really insanely small. So just like this. All you want is just to be able to see the line. So this makes the text objects really small. So now again, we're going to calculate the path going from 0, 0 to wherever the mouse is. So if I place the mouse, for example, on this position, then we should be able to see the path going from here to here and then making a diagonal from here to here. Okay, so if I'm here and I press on T, and yep, there you go, there's the path, starting from there, going there, in there. By the way, the line that we see down here, this is not the path, this is actually the canvas. So on the gizmos arrow, over here there's a search bar, you can search for canvas, and let's actually hide the canvas gizmo. Okay, so you no longer see that line. So now once again, if I place the mouse here, press on T, and yep, there you go, that is a path. So it goes from here to here to here. And if I put over here and press on T, yep, there you go, the path goes from here to here. All right, awesome. So with this, we can see the pathfinding is indeed working. So I can place the mouse anywhere, press the button, and there you go, the unit automatically calculates the path to get there. And of course, like we saw for all of the grid debug objects that we did, we can actually look at the internal state of them. So the one that we have on the top left corner, this is the G cost. Then on the lower right, this is the H cost. And over here, we have the F cost. So let's put the mouse here and press on T and see all the values. So as you can see, the G cost, this one is constantly increasing. So on this one, we've got 0, then becomes 10 since we have a straight movement. Then if we had straight movement over here, we've got 20. But a diagonal going there, we have 10 plus 14, so we have 24. And on the contrary, we have the H cost. So this is going to be the heuristic to reach the target. And actually in this case, since we have no obstacles, the H cost will actually perfectly match the G cost. So the H cost starts off at 24. So that is a guess of going from here all the way to there. Then we go over here, the H cost is 14. And over here, the H cost is the final node. So this one is 0. And the F cost is simply adding the G onto the H. So G plus H, and we always got 24. So as you can see, everything is working perfectly, and you can look at all the values in order to see that the algorithm is working perfectly. All right, awesome. So here we implemented the A-star pathfinding algorithm in order to find a path from point A to point B. As you can see, the algorithm isn't really all that complex. Once you understand how it works, it's actually quite simple. Now, of course, the main goal with pathfinding is to actually find a path from point A to point B while avoiding obstacles. So in the next lecture, let's add some obstacles and make some nodes unwalkable.